Hello, my name is Alexandre Desbarats, and I will present a review of activities conducted in Year 1 of the Environmental Geosciences project entitled Cumulative Effects of Resource Development on Mining Impacted Watersheds. The watersheds we're studying are in the historic cobalt mining camp of northeastern Ontario. Why study cumulative environmental effects in the cobalt mining camp? Well, the camp saw almost 90 years of continuous silver mining activity throughout the 20th century. This mining was carried out with virtually no environmental regulatory oversight. As the name of the camp suggests, cobalt was an important byproduct of silver mining. Today, cobalt is used in rechargeable batteries, which are essential components of many green technologies such as electric vehicles. This has prompted renewed exploration interest in the cobalt mining camp. So the challenge for proponents and government regulators is, how do you go about assessing the environmental impacts of new mining activity against a background of pervasive contamination from legacy mineral resource development. Our team consists of scientists from the Geological Survey of Canada, as well as Suzanne Beauchemin from Health Canada, Tom Al from the University of Ottawa, Heather Jameson from Queen's University, and I'm pleased to say we were joined this year by Danielle Fortin from the University of Ottawa, and Jennifer Cole and Richard Goulet from CanMet Mining. When assessing cumulative environmental effects in a historical mining camp such as cobalt, undergoing a new exploration boom, there are some key scientific questions that come up. Perhaps first and foremost is, how do you assess environmental effects of new mining development against a brownfield legacy of pervasive contamination? Another key question: what was the pre-mining geochemical baseline of the soils, sediment, vegetation, and waters of the cobalt camp? Has the existing environment reached a new geochemical equilibrium after historical resource development? Are there geochemical thresholds or tipping points that need to be considered in assessing cumulative effects? Can lake sediment cores or tree rings provide a reliable chronology of different phases of resource development? With reference to climate change, what effects will the environment have on past, present, and future development? Our project is subdivided in a number of thematic tasks. And in the following slides, I will review those tasks where we were active this past year. The most fundamental task has been to build partnerships with the local mining industry, more specifically Ag-Ni-Co Eagle Mines and First Cobalt. We met with Chris Kennedy, representative of Ag-Ni-Co Eagle, and their local consultants, Story Environmental. We presented the project and solicited feedback. As a result, we've obtained permission to access all their properties, and we've been offered the possibility of accessing their environmental data sets. We've also reached out to Frank Santaguida, Vice President Exploration for First Cobalt. We've presented our project, and we've obtained enthusiastic support and permission to access all their properties. Task 1, Metalloid loading and groundwater discharge to surface waters. This past year, we were active in Task 1.2, which is concerned with the discharge of metalloid impacted groundwater from mine openings. We conducted a field reconnaissance to locate sampling sites for mine-impacted groundwater, such as flooded shafts, adits, diamond drill holes in both the cobalt and silver center areas. The map on the right shows the distribution of the numerous mine and mill sites scattered throughout the to the Cobalt camp. Task 2 is concerned with the stability of legacy contaminants in wetland and lake environments. 2.1 is concerned with the sampling of mine wastes, sediments, and surface waters upstream and downstream of mining impacted areas. And this past year, we sampled surface waters from 6 locations in the Farr Creek watershed, which drains the cobalt mining camp. We collected 5 push core samples of sediments and tailings along the Farr Creek drainage, and we've analyzed the solids and pore waters from these samples. This slide shows some preliminary results from the surface water chemistry survey. We see a satellite image of the Farr Creek drainage, which extends here from Brief Lake in the the lower left-hand corner of the slide to Lake Temiskaming in the upper right-hand corner of the slide. Looking at arsenic concentrations along the drainage, we see that they are quite low in Brief Lake, but rise significantly in Cobalt Lake, which is surrounded by historical mining operations. For reference, the arsenic concentration in unadulterated mine drainage is over 700 micrograms per liter. Way downstream in Farr Creek, near its outlet at Lake Temiskaming, the arsenic concentrations are still elevated at 301 micrograms per liter. I draw your attention to the red dots, which mark the locations of push core samples. And in particular, we'll see results on the next slide from the push core sample in the Farr Creek Wetland. This slide shows geochemical profiles of metalloid concentrations in mine tailings. We see for arsenic and cobalt that pore water concentrations are at their highest at just below the sediment water interface, whereas solids concentrations are highest at a depth of 30 to 40 centimeters below the interface. For nickel and antimony, on the other hand, peak pore water and solid concentrations seem coincident at the same depths. This suggests that there are different metalloid remobilization processes in tailings profiles. Task 5 is concerned with the weathering processes in cobalt-type arsenide tailings. This past year, we were active in tasks 5.1 and 5.2, which were concerned with field sampling of in situ weathering products of arsenide and sulfide minerals in the tailings, and detailed mineralogical investigations of weathering products and laboratory studies of metalloid mobilization. We successfully recruited a promising master's student candidate, Cole Fisher, who will be advised by Tom Al and Danielle Fortin at the University of Ottawa. His research topic is concerned with the geochemistry and geomicrobiology of the Cart Lake tailings. This past year, we started with a field orientation and a study site selection, which led to the selection of the Cart Lakes tailings deposits. Fieldwork started at Cart Lakes with the sampling of tailings pore water and the taking of horizontal tailings cores to analyze for microbiological activity. Laboratory work so far consisted of mineralogical analyses of the tailings. So for further information on our project, please don't hesitate to contact me, Alexandre Desbarats, at the phone number or email address shown on the slide in front of you. Thank you very much for your attention.